What happens when a computer scientist, a data scientist, and a law professor walk into a bar? I'm here to tell that tale. Hello, everybody. I'm Supreet, and here to present our work on understanding and benchmarking the impact of GDPR on database systems. Okay, first things first, what is GDPR? It's a European law passed in May 2018, which grants that the privacy and protection of personal data is a fundamental right of all the European people. It's written in 99 legal articles that regulate all aspects of personal data from the point of collection through deletion. It grants 8 specific rights to the people of Europe. We're going to get to that very soon. And it also assigns explicit responsibilities to the companies that collect and process personal data. And whenever there is a violation, it levies hefty penalty on these companies. As you might have seen in the news, the first 2 years of GDPR rollout have been quite disruptive on the companies. Several of them had to shut down their operations in Europe. Many had to change their business practices. There were several multi-million-dollar penalties on companies such as Google, Marriott, and British Airways. And just in the first year of rollout, complaints were received against nearly 150,000 companies. So what's going on? GDPR compliance has been a challenge for several reasons, but one of the fundamental reasons has been around the construct of personal data. So what is personal data? GDPR has a deceivingly simple definition. Any information that relates to an identified or identifiable person is personal data. Okay? So to make that concrete, let's take the example of our favorite professor, Dumbledore. And there is a company, Three Broomsticks, which is interested in his personal data. They collect 3 pieces of information: that Dumbledore has a phoenix as a pet, he drinks coffee at 8 a.m. and has published a paper at VLDB 2020. Okay? So when you look at these 3 pieces of information, none of them in and of themselves identify the person. Okay? In fact, one of them is wrong. But what GDPR says is that as long as this information is stored associated with a person, it becomes personal data, right? So the generality of this definition, combined with the fact that GDPR is not specific to any one particular domain like health or education, it brings virtually all companies that collect and process personal information under its foray. When that happens, GDPR says Professor Dumbledore has 8 rights. He has the right to know what is stored, to access and download that information, to rectify any errors, to request for deletion, to object any of the data being used for any specific purposes, to port them to a different controller, so on and so forth. And on the controller side, the 3 broomsticks have to obtain consent, track how the data is used, keep it secure, notify any data breaches, etc. Okay? So the focus of our project is on the database system that stores this personal information. Specifically, we asked the question, how do we build a database system that stores personal information in a GDPR compliant way? We go on to do this in 3 steps. We analyze, we take the GDPR articles and translate them into system level characteristics and capabilities. Then we build and we measure its impact. Okay, so the actual analysis is quite lengthy. So I'm going to focus on 2 examples and then I will generalize our findings. Okay, so the first one is to store the data with a clear timeline for deletion. This stems from Article 5.1e, the storage limitation, which says that data should no longer be kept than necessary for the purpose for which it was originally collected. Also from Article 17, which is the right to be forgotten. So to implement this in a database system, it basically translates to us having to store a time to live or a TTL value along with every personal data, as well as the ability to do a timely deletion. Next one is to keep record of data processing activities. This comes from the namesake Article 30 and also from Article 33, which says that in case of a data breach, the affected party as well as the regulator should be notified within 72 hours. So what should the database do to achieve this? It should keep an audit trail along with the personal data, indicating how it was used and by whom and for what purposes. Should also have the ability to monitor and log in a fine-grained fashion of all the personal data accesses. Okay, so we did this across all the 99 articles, both individually and collectively, and identified a set of attributes and actions. Okay, so these behavioral attributes, there are 7 of them, we call them GDPR metadata. And in terms of actions, there are 5 features that need to be implemented. Okay, encryption, fine-grained monitoring and access control, ability to timely delete, and metadata-based querying. So our hypothesis was that GDPR metadata would lead to storage overhead. This is because if we need to store with every piece of personal information, 7 pieces of metadata, it would lead to storage overhead. In terms of capabilities, if we implement these features, and then the data path and the control path operations would experience considerable overhead. Okay, so we went on to implement this in 2 widely used open source systems, Redis and Postgres. So the table here shows the set of features on the in the first column and how we went on to do in the next 2 columns. If the database already had that feature, we just went on to configure that, indicated in green. If it could be managed with external scripting and third-party libraries, we did that, indicated in yellow. And if neither of these was an option, we actually implemented that via code changes, indicated in red. Okay. So to measure how this impacts these 2 systems, we used YCSB, and we observed that Redis performance went down by 80% and Postgres by about 50%. We have more details about this in the paper, but I'm going to switch to a more interesting question where we ask how these systems perform against actual GDPR workloads. It so happens that there was no workload, there was no benchmark that measured GDPR workloads. So we went on to build one called GDPRbench. I'm going to describe its workloads and its metrics so that we understand what we are measuring. Okay, so remember from the GDPR ecosystem, there's a database at the center, and there are 4 actors that interact with it. The company that collects the information, they manage and administer the database. The user will exercise their rights. The regulator will audit and investigate the activities. And there's a processor which will do data analysis on behalf of the company. Think of this as Google Cloud and outsourced companies that do processing. Okay, so based on our understanding of the regulation, as well as what went on in the last 2 years in terms of legal precedents, we identified and defined 4 workloads: controller, customer, regulator, and processor, and defined their characteristics and the arrival distributions and so on and so forth. We also identified 3 metrics: correctness, completion time, and space overhead. Okay, now let's switch over to our compliance systems and see how they performed on GDPRbench. On the left, I show Redis, and on the right, I show Postgres. In terms of space overhead, Redis experienced 3.5x. This means that for every byte of personal data that you put in the database, the size of the database increases by 3.5x, including the metadata. Okay, Postgres experienced an overhead, space overhead of 5.95x, and this extra is because we configured multiple secondary indices for metadata so that the query response time is faster. And the benefit of this overhead will be evident in the completion time graph, which I'm going to show now. On the y-axis, we have the completion time, and on the x-axis, I have the 4 workloads for GDPR: the controller, customer, processor, and the regulator. Okay. So as we see, the patterns of the bars are sort of similar, but I want you to focus on the y-axis. In the first graph, it runs from 0 to 200, and for Postgres, it runs from 0 to 20, right? So there's an order of magnitude. And we've seen this trend across multiple experiments we did where GDPR workloads run faster and scale better in RDBMSs as opposed to the NoSQL databases. Our work had several takeaways for database administrators, engineers, and designers. Okay, so the first is that GDPR compliance may result in high performance overheads. Even when the system features are natively supported, production systems should be carefully analyzed before these features are enabled. Second, compliance was easier in RDBMS than in NoSQL. So in our case, Redis needed much more involved changes, and it experienced much higher overhead compared to Postgres. Finally, GDPR compliance is a spectrum, right? So the law allows for interpretation of the actions that are expected by the company. So this results in rich trade-off between the strictness of compliance versus the efficiency. In our case, in this work, we assumed a stricter compliance, but it's a trade-off. It's a spectrum. So the companies and the database administrators could choose the point that they're comfortable with. Okay. With that, I would like to thank you for your patience, and you can find out more about the project at gdprbench.org. Thank you.